Okay.
Professor, I have a question here.
Yes.
You said like when it goes above B, then we sell it, right?
Yes.
When do we buy it? Below A?
If it goes below A again.
Okay.
So in the graph, so we buy here because that's the first time it goes below A again. So whenever it goes below A, then we buy. Whenever it goes above B, we sell. So at least this amount of B minus A will be the least amount of earning for any oscillation.
Then why C3 is equal to 1 then?
Why?
Because
What is 1?
why C3 equals to 1 in the graph here?
Because C3 has to be 1 because C3 is what? C3 is multiplied to, so C3 will be multiplied to X3
X3
minus
minus X2.
right?
Yeah. Yeah.
And here, what is, so this is X0, X1, X2, X3. So this jump is X3 minus X2, and that jump is our earning because C3 is multiplied to that difference, and that difference multiplied to C3 is has to be there. Is it?
Yeah.
Good?
Yeah. Makes sense. Thank you.
Okay, so our YN is a martingale. Therefore, it looks like we are keep earning. We cannot lose, but we lose also because YN expectation must be 0. We know YN has an expectation 0, right? So let's estimate this YN. Let's define UN of AB. So that's the notation I define to be the number of up crossing up to xn. So just consider x1 to xn. Then here in this particular case, we see, so I called it up crossing if I move from A to B. So I see 2 up crossing in this example, right? And UN is I define to be the number of up crossing up to n. Does it make sense, right? Okay. And we want to estimate how many up crossing can happen in average. So YN, so whenever there's an up crossing, YN will be YN will increase at least by this amount. So the least amount of so whenever there's an up crossing, there's an earning at least by B minus A. So if I multiply this by the number of up crossing, that's the lower bound for YN. But that's not true. This is not true. Why? Because even though there's 2 up crossing, so in the above example, this is true. Above example, for YN is here, if N is only showing in this graph, then YN for this final N is exactly satisfying this inequality. So up crossing is 2, so B minus A times 2 is of course smaller than our earning by Y. But this is not true because it may keep going. So what if it goes below somewhere here? Okay, then you have to buy it here, sell it here, and buy it here. And then everything from here to here is also our earning, which is negative. So even though up crossing is just 2, we can have very much lose. So we have to consider such possibility, such huge loss. So what is such loss? This loss can be the final position xn, and so this loss can be as huge as this amount, xn to the difference of a. I mean, this difference can be approximate loss amount, right? But of course, this loss amount is smaller than xn minus a because it always starts slightly below a. So if I subtract like that, then it will be still lower bound. Am I making? Yeah. And this is the case only when xn is below a. So that's the bound for yn. This is the upper bound for yn. Good. Since yn is a martingale, expectation of yn is 0. And from that, we can obtain the expectation of the upcrossing. Yeah, let me write down the full expression. Minus the expectation of sorry, I charged for 30 minutes before the lecture, but still. Sorry, just 1 more minute charging. Now I think the reason, maybe the charging doesn't work. So once I started using the Apple Pencil, maybe the charging works. Charging. Okay, so let me just wait until it becomes 9:47, then I will restart.
Oh, Prof.
Yeah.
Please, once it goes below A, in the last example you gave, and we buy,
Yeah.
and then it goes just a little up, and we sell.
Yeah.
No.
Oh no, we don't sell.
No, we don't sell. We don't sell. Yes.
Yeah, you're
yes,
right. You don't sell. Why we sell? I'm sorry. I was wrong. You're right. You're just correcting me that part, right?
Yes.
Yeah, you're right. I'm crazy. So yeah. So I said
just a little bit above A, we don't sell.
Right.
But
It's still below B, so we don't sell. Yeah.
Yes. So when it comes down to xn, then we start losing.
Yeah. Yes. Okay. Now let's restart. So yeah, you exactly correct. I was out of my mind as always. This we don't sell. Okay. So let's take the expectation on the other term also. So we get this inequality, which less than 0 of this summation, meaning that b minus a, this thing. So let me just write with just un, not including a and b, is bigger than expectation of this. So we obtain this inequality, right? Oh, did I? No, I make a mistake. I made a mistake. I'm sorry. So inequality is opposite. Okay. Now, if we will make an assumption. Not assumption. If we assume expectation to be bounded. So that's meaning L1 norm is bounded. So what I wrote is L1 norm, which is meaning the integrability of this random variable, the integral of xn. If this is bounded, so if this is smaller than some number for any n, then the right-hand side becomes, then the right-hand side can be also written as expectation of xn plus expectation of a using triangular inequality. So let's say this is bounded, meaning some number. So this is bounded by some number plus a, which is again another number. Which means b minus a, I don't know, expectation number of upcrossing is bounded by some number, right? Because it's m plus a divided by b minus a. So anyway, some number, m tilde, finite number. And un is un is of course only increasing in n, right? Un is also, yeah, of course, yeah, expectation of un is also increasing, only increasing in n, it cannot decrease, which means the limit also bounded. So number of upcrossing cannot go to infinity. Number of upcrossing is the number of crossing is, let me see, the number of crossing. Yeah, let me use this notation. Number of crossing at infinity. Number of crossing at infinity is bounded by m, some number, finite. So expected number of crossing for infinite time is finite. So this u infinity is certain random variable. So it's a function. It's a function in the big sample space. And if you integrate that function, then it gives a finite area. That's the meaning of this statement. And therefore, that function cannot be divergent like in any interval, right? That function should be divergent only in probability 0 point. So almost surely, so if any function becomes finite integral, then almost surely u infinity is finite. So what this means is that almost surely, whenever you have a martingale thing, this number of crossing is finite, even if you wait for infinite time. Okay, that's the partial conclusion. And here, important thing is this condition. So if the L1 norm is bounded, almost surely the number of crossing is finite. So let me just rewrite this statement. So xn is the martingale, and such that this is bounded by m. And okay, and number of crossing almost surely finite. So here's martingale. Okay, so this is up crossing lemma, which we will need it for proving martingale convergence theorem. Okay, so now let's start proving martingale convergence theorem. Martingale convergence theorem. So again, Xn is the martingale. And we will use this condition because I want to use this upcrossing. So that's bounded. So I can rewrite this as primum is finite. That's the same thing as primum is finite means n is bounded by some number n. Okay, then the statement of the convergence theorem is that the limit exists, the limit of xn and infinity exists, and this is so this exists almost surely. So limit exists if the so limit does not exist if it keeps oscillating. So what we want to show is the basic idea is almost surely the oscillating never happens infinitely many times. And that's exactly the upcrossing lemma. Upcrossing lemma says that oscillating between A and B only happens finite time. It cannot oscillate infinitely many times. And that's the meaning of convergence. So not convergent means oscillating, keep oscillating, right? Okay, so that's and for the second statement, so there's two statements. So the limit is also integrable. So that's the statement of the martingale convergence theorem. So let me emphasize that this convergence is almost sure convergence. Yeah, I'm emphasizing because that will be related to our quiz today. Okay, let's start proof. Proof is also interesting. So let's define the set which is not convergent. So this is the subset of omega, which represents all the case where not convergent. So what is the set not convergent? It's those sample where the limit doesn't exist, which means the lim inf. So limit doesn't exist, so it oscillates till infinity, which means lim inf and lim sup, they are not equal. So if it oscillates, the lowest possible value that showing up in the oscillation is the lim inf. The highest part of the value that show up in the oscillation is lim sup. And if they are different, then that means no limit. If they are not equal, and of course lim inf cannot be bigger than lim sup. So if this is true, then it's exactly characterizing this non-convergent case. Okay, so whenever a certain number is less than the other number, you can always find infinitely many rational numbers in between. So I will plug in rational number in between. P and Q, P and Q. So you can always plug in some rational number in between. Of course, depending on where the lim inf is, you have to define, choose different P and Q, right? Different interval gives different P and Q. But anyway, you can always find P and Q. So if I consider all the possible P and Q, all the possible rational number P and Q, then that will be exactly above the same set. So for any lim inf and lim sup, you can always find P and Q. And therefore, if you consider all the possible P and Q that satisfy this, then that's the same set. I'm taking the union, meaning that we consider all the possible P and Q. Does it make sense? And the reason I did this way is because P and Q are rational number, so there are only countably many of them. And because, and therefore this union becomes countable union, and all the probability theory is, you can add probability only for countable union. So, okay, so let's, and let's again define this new set. This is the set, let's say, lambda of PQ. So once P and Q is defined, then this is the event where X and lim inf is less than P, lim sup is larger than Q, So that's my definition. And you can see that, so what is the probability of this event, lambda PQ? So lambda PQ is, so lambda PQ means that lim inf has to be less than P, lim sup has to be larger than Q, which means it should oscillate between P and Q infinitely many times. It should oscillate between P and Q infinitely many times, which means the upcrossing number around PQ is infinite. That's exactly this lambda PQ. So lambda PQ is given by this event where the oscillation around PQ is infinite, so crossing number is infinite. Is it true? Yeah, that's true. But why did I wrote here inequality? No, I think there's no inequality. It's equal. Because if the upcrossing number is infinite, then it should come below P infinitely many times. It should come above Q infinitely many times. So lim inf should be less than P. Lim sup should be bigger than Q. Yeah. Okay, and what we know is that this is 0 by upcrossing lemma. Because almost surely the upcrossing number of upcrossing is finite, cannot be infinite. So the probability of infinite upcrossing is 0. Okay, and therefore probability of lambda, which is of course less than the probability of lambda PQ summation over all the PQ, right? Because the lambda PQ union is lambda, but lambda PQ, of course, they have intersections, non-zero intersection. Therefore, generally, the probability of summation of the lambda PQ will be greater than probability of lambda. And this is still 0, because each term is 0. That's the one of the defining property of the probability measure P. Probability measure P is defined such that yeah, you can yeah, one of the property was if certain thing is countable disjoint union, then the probability of such event is given by the summation of each probability, right? Okay, so we show that the set lambda has probability 0. What was set lambda? Set lambda was no convergent set, right? Yeah, not convergent. Not convergent set has probability 0, meaning with probability 1, xn will converge. So I can okay. xn converges to a certain number with almost surely. That's what we just showed. Any question? Okay, so we can define x infinity, of course, limit by the limit. And that's if that definition is now good for almost sure set. But since this definition doesn't work for some tiny set which has probability 0, let's use lim_int to define for every point. So x infinity is defined by this one. And of course, this is lim_int is equal to limit for almost sure set, for probability 1 set. Okay, and let's prove the final statement about x infinity having finite L1 norm. So this is given by expectation of the lim_int should be inside the absolute value, but I put it outside. Lim_int should be inside the absolute value, but I put it outside. Will it change the inequality like that? So what's accurate is So far this is true. Yeah, right. So this will be smaller than no. Um, mm, mm. Yeah, but right, uh, but we already showed that this convergence is almost sure convergence. And whenever we take the expectation, lim inf and limit doesn't so the only part that lim inf and limit is different is probability zero part. So it doesn't affect the integral. So that's this one. And therefore, this is equal to, and I mean, this is equal, not equal. And this is also limit xn and going to infinity. What's yeah, if certain sequence converge, then its absolute value also converge, will be the same. And finally, right, and then this is less than a limit of expectation and going to infinity. So the final inequality is coming from Prob2 lemma. Of course, Prob2 lemma is for lim int. But in here, the lim inf, we can change both sides by lim inf without change. So this is equal to lim inf. This is equal to lim inf because the only difference is the measure zero set. And using the Prob2 lemma, this will be lim inf. Of course, lim inf is less than limit, but anyway, we use this is bounded by certain large number m for any expectation of xn. Therefore, lim inf should be also bounded, and that gives the proof. Okay, so we show that almost sure limit exists, and the limit is also integral. So that's the martingale convergence theorem. Okay, so we reached the goal. And so for the remaining time, I will give some example about martingale. Okay, any question? Okay, I want to have some simple application, a little bit related to finance. So before introducing the application, let's start by small lemma, some simple fact. So let's use omega to be very simple set, just two elements. And I define the probability measure on here to be so one has the probability 1. So the event only contains 1, has probability 1. And of course, then the other event -1 should have the probability 1 minus p. Okay, and let's notation. Okay, I can use xn. So xn is either so xn is a random variable. I am defining a random variable, and I define a trivial, random variable like this. So I don't know this this way of writing. Yeah, I'm sorry. So I think it's better to write in this way. So consider random variable xn just having 1 or -1 with probability 1, probability p, and with probability 1 minus p. So they are identically distributed and independent. Okay. So this have mean, what is the mean of this random variable? It's 1 times p plus -1 times 1 minus p. So the mean is 2p minus. Okay. Sorry again. Probably one more charging will last the remainder of the class. So I will define expectation of xn because I want to consider martingale. Martingale is where the expectation stays same, but I want to make it stay at 0. Just one more minute. I'm just waiting the 1020 becomes 1021. Okay, now let's start again. So the expectation is 2p minus 1. Therefore, if I subtract xn minus 2p minus 1, then that's 2p minus 1, like that. Then it's the random variable with mean 0. Right? Okay, and then I will, yeah, actually, I will change this n to be k because I want to sum the whole thing. Sum the whole thing by k from 0 to 1 to n. Okay, so those xk minus 2p minus 1, I will consider as some increment, and I will define Zn by this random variable. So Zn is a martingale because Zn and Zn minus 1 have the same expectation. Because the difference is exactly xk minus 2p minus 1, right? And those have mean 0. So increment is 0, therefore the mean of Zn is preserved. So this is martingale. So Zn and from 0 to infinity is a martingale. Okay, and the following lemma is and let's call M is another martingale. Let M n be a martingale such that Mn is Fn measurable. So martingale is measurable with respect to filtration, you know. Fn is measurable, and Fn is coming from this sigma algebra for Zn. Meaning that if you know Zn, if Zn is known, Mn can be found. So Mn and Zn shares the same information. So if Zn is determined, then Mn is also determined. Mn is a random variable, but if Zn is determined, Mn is determined. Okay, if such thing happens, then it turns out that Mn is equal to M0 plus martingale transform of Z. So what is the martingale transform? There exists certain pre-visible sequence. So here let's use different, I usually use C for the pre-visible sequence, but here let's use H. No, I'm going to use this, stick to the same notation. So C, Zk minus Zk minus 1. So that's martingale transform, right? So K from 1 to n. So usually the martingale transforms, yeah, right, good. That's the martingale transform. for some pre-visible sequence, CK. So meaning, it means that CK is FK plus K minus 1 measurable. That's pretty, just I forgot. CK is, yeah, K minus 1 measurable. That's okay, meaning that whenever there's another martingale, which can be determined if the martingale Zn is determined, then those two martingale can be represented by one another by certain martingale transform. So you can find CK such that this is true. So then, okay, so okay, so okay, so Mn, this is Fn measurable, which means if Zn is determined, it will be determined. Zn is made out of x1 to xn. So Mn will be determined if Zn is determined, and if x1 to xn is determined, then Zn is determined. So Mn will be determined in terms of x1 to xn. So it will be function of certain function of this. So Mn is a random variable, but it's certain function of x1 to xn, and here capital X1 to xn is a random variable, and that's the meaning of Mn being Fn measurable. So there exists certain function. Okay, so what we want to do is using the martingale property, Mn minus Mn minus 1 with conditional probability, this has to be 0. So Fn, its conditional probability with Fn minus 1, meaning that x1 to xn minus 1 x1 to xn minus 1 can be so in this sigma algebra Fn minus 1, xn is not random variable. Xn has to be one has to average xn, because xn is not measurable in terms of Fn minus 1. So you have to average over xn to get rid of that. So we will average, so first term is this one, and the second term is this one. And in the first term, we have to average over xn because of this conditional probability. So what is the average? So xn can be either 1 or minus 1. So it's x1 to xn minus 1, 1, or minus 1. The probability to be 1 is p, probability to be minus 1 is 1 minus p. That's the first term. What's the second term? Second term is expectation of, that is defined, and that is just same as m minus 1, conditional probability. And we define that to be fn minus 1, x1 to xn minus 1. So just using this definition of here. Okay, and then I will collect this way, x1 to xn minus 1, 1 minus fn minus 1, 1 to xn minus 1, plus 1 minus p, and then I collect also the similar thing with a minus 1 at the end, minus fn minus 1. Does it make sense? Okay, so this means that these two terms have satisfy the following. So fn with 1 at the end over 1 minus p is equal to fn with minus 1 with p. That's same. And both, if you look at both one, what is the random variable that show up? It's x1 to xn minus 1 here, also x1 to xn minus 1. So all of them, these are fn minus 1 measurable. These two are fn minus 1 measure, right? I will multiply both sides by 1/2 so that I have 2. And then this I will define to be Cn. That's pre-visible because it's fn minus 1 measure. So that's my definition of pre-visible sequence Cn. Then it should miraculously hold true. So let's show that now this Mn is given by m0 plus, so claim that's ck zk minus ck minus 1 k from 1 to n. Claim 0. Okay. So to prove that, we only need to prove the following. So mn minus 1 is cn zn minus zn minus 1. Then by induction, this is true, right? So enough to show. Okay, so mn minus mn minus 1 is already we wrote down as fn of blah 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 to xn plus xn minus fn minus 1 to xn minus 1. That's the left hand side, and on the right hand side we have this one. So let's check whether it matches the right hand side for both xn equal 1 and xn equal minus 1. So the left hand side, if xn equal 1, then the left hand side becomes this fn 1 minus fn Fn minus 1, Fn minus 1, which is exactly the numerator here. So I can rewrite this one as Cn times 2 times 1 minus p, right? And this 2 times 1 minus p is equal to I forgot what is the definition of Cn. Yeah, Cn is the summation of here. So if I put xk, xn to be 1, then that's equal to, this is equal to 1 minus 2p minus 1. Is it true? This 2 minus, is it true? Yeah, that's true, right? That's true. So this is exactly xn minus 2p minus 1 when xn is equal to 1. So it matches. So this part is exactly Zn minus Zn minus 1. Therefore, Cn times Zn minus Zn minus 1. Checked. Got it? So if xn equal 1, then it's true. Again, we do the same thing. If xn is minus 1, then the left-hand side becomes the same thing with the minus 1 at the end, fn minus 1 done. So now I see this thing showing up. So it's minus 2p times Cn. And minus 2p is also minus 1 times 2p minus 1. I hope that's right. Yeah, that's right. Which is exactly, again, xn minus 2p minus 1 when xn is minus 1. Okay, so we just check this equality, and therefore this claim is true. Okay, so that's simple lemma. I guess we will use it for some application in finance. So I am not at all expert in finance. I'm not even doing it. I never bought stock in my whole life. But my friends are all expert. They all work in finance. End up working in finance. My friends during my I majored in physics, and it's quite trend in modern society that many of the math or physics major, they go to finance. So my friends also follow the same. So they mostly in finance, and when they start changing their major into finance, they talk a lot about Black-Scholes equation, Black-Scholes formula. So it seems that's quite important in finance. And since I found some simple example about this discrete Black-Scholes, with this title, discrete Black-Scholes formula, I want to give an example about that. And it's also called option pricing. I have very, very childish concept about this option pricing. So let me just explain about that. So there's two different kinds of investment. You can invest in the stock. Stock, you can gain a lot, but there's a danger, right? So stock going up and down randomly, so you can gain a lot, but there's a danger. There's more stable investment, which is bond. It seems after reading it, so bond seems to have fixed interest rate. So with fixed interest rate. If it is not, then we just consider this to be investment with the fixed interest rate, rate R. So if you put some money into the bond, your money increase with multiplying by 1 plus R. But stock, you can have so let's consider bond to be Bn. So Bn is the, so let's consider n to be that, like the number of days, or so I will consider discrete Black-Scholes equation. So we only consider the stock price or bond in discrete time limit. So Bn is the price from the bond at time n, and that's keep increasing from the original price of the bond by interest rate R. Good. For the stock, the price of the stock is a random, so Sn, that's the stock price. Stock price at time here I use time interval n to n plus. Also here at time interval n to n plus. So that's the bond price, the value of the bond. So you can either buy bond or buy stock. If you know for certain that stock price is going down or it's going up not as great as the bond interest, then you should buy only you should only buy bonds. If you know the stock price will go up much faster than the interest rate of the bond, then you should buy this whole stock, right? But since you don't have any specific knowledge, you have to buy both of them with certain ratio. So you buy certain number of stock and you buy a certain number of bond. Number of stocks you bought at time. What's the time? At time n, and that's the number of bonds. Time n. Okay, so let's start from actually start from 0. So you first buy bond and stock at time 0, like this. So you have some money X. So you buy certain number of stocks and certain number of bonds. Okay. And then stock price will change. So the stock price will change. So they just okay. Yeah, I don't know. Yes, somehow the initial time is not 0 but 1. Okay. Okay, then at time 1, the stock price will change into S1. And the bond price will change to B1. So you gain how much? You gain A1 is 1 minus S0 by the amount of the change in stock price, and also by the amount of change in the bond price. That's your gain, right? So that's your new price X. Yeah, okay. So that's the X X1. Let's see, this is X0. So X0 is the starting the amount of investment, and then after the next one you get X1. Good. And X1, you have your whole money X1, and then you can redistribute your money between stock and bonds. So you redistribute into like that. So you redistribute your money. So instead of buying A1 of stock, you can buy with the same total amount. You buy A2 of the stock and B2 of the bonds, but the total has to be same. So you redistribute, and this this strategy by which one, how much you buy for which one, and how much you buy which one. So this strategy A1 B1 is the strategy. Oh, I go over time, and this strategy is called portfolio. That seems to be used a lot. Yeah. By the way, I think I have to stop. So we will keep talking about those portfolio, how to invest using 2 different methods of investment, how to mix. Okay, so any question? Okay, otherwise, let's see next time.
Quiz is on, right?
Yeah, quiz should be on, and it's about this martingale convergence theorem being exists in almost sure sense. Good.
All right.
Thank you. Have a
Okay,
good day.
thank you, Prof.
You too.
Thank you. Have a nice day.
You too. Bye.
Thank you. Bye.
You. Were you able to? Okay, bye. You think I will disconnect? Stop share.